Welcome everyone. It's a great pleasure to have here Professor Levon Pogosian today. Thanks a lot for accepting our invitation. Levon received his PhD from Case Western Reserve University. He was a research fellow at Imperial College in London, Tufts University and Syracuse University before taking on a faculty position at Simon Fraser University, where he is now professor of physics. He's a theoretical cosmologist working on a broad range of topics that can be collectively described as using cosmological observations to test fundamental physics. He's particularly interested in cosmological tests of gravity and dark energy, cosmic magnetic fields, and other relics of the early universe, as well as the topic of the Hubble tension and other cosmological tensions that have emerged in the recent years. Today, he will present sound-horizon-agnostic approaches to the Hubble tension and an update on primordial magnetic fields. Levon, please, you can start when you're ready.
Thank you very much, Eleonora, for this kind invitation, and also for all your efforts, along with Jackson and Emmanuel, running this series and organizing the community, working on cosmological tensions. So my talk today will cover some of the work I did recently with my collaborators, Karsten Yudamzik, Gongbo Zhao, and also two very talented PhD students, Helena Garcia Escudero and Hamid Mirpurian. In particular, I'll mention a recent paper that was submitted a week ago with Helena and Hamid. And I guess in this audience, the topic of the Hubble tension is well reviewed and understood. So I'll start with just a very short statement of my kind of view of it. When I see this plot that was made by, I guess, Eleonora, or in a paper that she led some time ago, but the situation hasn't changed significantly since then. And you can clearly see two clusters, two columns that kind of signify the tension. There are two groups of measurements. The one on the left corresponds to smaller values of the Hubble constant led by the measurement by Planck and now by other CMB experiments. And on the right are sort of the more direct measurements led by the tension, basically is led by the Cepheid calibrated supernovae from SHOES. And when I look at these two columns, what I observe is that the tension is between measurements that rely on knowing the sound horizon or using a model to compute it in order to interpret the data, and measurements that do not. And that for me is a hint that something interesting could be happening at the epoch of recombination that's relevant for the model of the sound horizon. And I'm obviously not the only one who observed that, but that's my starting point for this talk. And just to build up to my subsequent points, let me review a little bit about how we learn the value of H naught from CMB and BAO. So starting from CMB, the main piece of information that we have is this angular size of the sound horizon, theta star. But on its own, it's not enough, right? So we need to know other cosmological parameters, but the main thing that we need to know is the value of the sound horizon at decoupling, which sets the period of these oscillations. And theta star, it's angular size. So if we somehow know the sound horizon, we can observe the theta and deduce the comoving distance to the redshift at which the sound horizon was set.
Levon,
and yeah.
George has a question. He wants to.
Hi, Lev. Just on the point about the sound horizon.
Yeah.
I mean, if you are willing to accept primordial nucleosynthesis, then that can give you a constraint that effectively fixes the sound horizon.
That's not quite true, because you still need to evolve your rekfast to compute it. You need to evolve the recombination model. So you're using a model to compute the sound horizon. And what you're using the BBN prior for is to set the value of omega b.
Right.
Right. But you're still using a model.
Okay.
So that's the main distinction in my talk, the distinction between the sound horizon being a derived parameter as opposed to a primary parameter. Okay. So, with CMB, you can deduce all the necessary parameters, all the information you need to deduce the sound horizon, as well as everything else that you need to compute the H naught. So the CMB spectrum, and even just the temperature anisotropy spectrum, has all the information you need. It has, you can deduce the densities of matter, radiation, baryon density, you measure the position of the peak, and these are 4 key parameters that you need to constrain all the parameters that appear in this equation for the sound horizon. And you do need a model as well for the recombination in particular, like RecFast or CosmoRec or other standard codes that are currently used to compute this value of Z star, which directly affects the value of R star. So in most CMB studies, in fact, to study the CMB spectra, you do need to derive R star from this model. Now, BAO is measuring the same physics, namely the acoustic oscillations in the primordial plasma, with the same physics, same sound horizon, but it doesn't have the luxury of being able to constrain all the other cosmological parameters. So BAO by itself measures the angular size of the acoustic feature at different redshifts, and by itself, without any input about the physics of the sound horizon or anything else, in a flat lambda CDM model, it can constrain 2 parameters, the product of RD times H and the capital omega. So a measurement of BAO at a given redshift gives you a blob, like you see in this plot from the DESI paper. And if you measure them at multiple redshifts, these blobs appear at different angles, and eventually you zoom in at a rather tight oval that gives you a pretty decent, very strong, in fact, constraint on RDH naught and omega meta. So in order to deduce H naught, you need additional information. I'll get to that in a minute. But even that measurement, which is quite independent of the physics of the sound horizon, appears to be in a bit of a tension with the values for RDH naught and omega meta deduced by doing a full fit to the Planck spectra with the sound horizon model included in it. So this is not a significant tension. Nevertheless, it's noticeable. We can see it by eye. It's about 2.3 sigma. And that's part of the evidence for dark energy, dynamical dark energy. So this is the source of that evidence as far as the BAO and CMB combination. So allowing for dynamics in dark energy allows you to bridge or alleviate this tension. And so that suggests a test. So we could ask, well, is it something wrong with the expansion of the universe that we need to fix? Or maybe it's something with the sound horizon physics that we need to adjust. And by the way, I just want to use this moment to apologize in advance to everyone who worked on this topic, because I'm not citing a lot of the very interesting work on this topic. So if you feel like your work is important to mention, please type it in the chat. But it's not for the lack of my interest in every other work. I just haven't included all the citations. So what is intention here? Is it the late time expansion history or the sound horizon physics? So one thing you can do is use theta star itself as a BAO point. So theta star is the angular size of the R star at redshift 1100 or so. And in fact, that value of redshift is not very important, whether it's 1100 or 1090. It's actually, at that point, the integral saturates, so the exact number doesn't matter. And we let RD to be purely free parameter, not derived. And we assume that the sound horizon at baryon decoupling and the sound horizon at the peak of the visibility function are related by a given ratio that's That's the same as in the standard lambda CDM model. And that assumption is very well tested in all other extensions of lambda CDM that modify the sound horizon. That relation doesn't seem to change in all the known models. So if you add the theta star, it provides another band, and that band passes smack on through the daisy band. So that tells us that at least as far as the geometry and acoustic consistency of the acoustic scales as measured by CMB and BO, there is no apparent tension. So if you combine the two, you get a tighter constraint on RDH and omega meta. And here, unfortunately, you can't see the colors very well, but you can contrast this RD agnostic way of doing it that I show with the full fit to Planck, which is that 2.3 sigma tension, which uses the information about RD. So this is not necessarily complete evidence, but it's an indication that it's not the expansion history that's the problem. There is no apparent tension as far as the geometry of the universe or expansion history, but it could be something with the sound horizon physics. Okay, so how do we get H naught from BAO? You could use the value of the sound horizon that you derived from CMB, for example, and analyze the BAO data. You could use the BBN prior on omega B, and that's what George mentioned earlier, to compute RD using the standard model and use it in your analysis of the BAO. And this top two currently agree very well. So that should be said. There's a very good consistency between the two methods. Another option, which treats RD as an entirely primary independent parameter, is to find another piece of information on the physical meta density, omega meta H squared, and use it to break this degeneracy between the sound horizon and H. So this has been pointed out in a few papers that I wrote with my collaborators. And one idea is to combine it with CMB lensing as well as galaxy weak lensing and clustering correlators, like 3x2 point correlations from the dark energy survey. Or you could do a consistency test. You could use a prior on omega meta H squared obtained from Planck and just see with that prior, do you get the same value of H naught or not? Let me first mention the BAO-CMB acoustic consistency test. So this is where we treat RD as a free parameter, and we put a Gaussian prior on omega meta, which is this number that happens to be close to the value obtained from a lambda CDM fit to Planck. But in a number of modified recombination models that I studied and other people studied, the same value more or less is the same. The value is more or less the same. So this is not very specific to lambda CDM. It covers a broad range of modified recombination models, which predict a higher Hubble constant. So with this sound horizon as a free parameter, with this Gaussian prior, we obtain an H naught, which is 69.4 plus minus 0.65 or so, with a slightly smaller value of the sound horizon by about just less than 1%. But and you can see here that there's a very good consistency between when we analyze BAO by itself, again, and after we add theta star. So the mean values don't shift. There's a very good consistency as far as the acoustic peak information is concerned, but there's a minor, maybe 2 sigma-ish difference, but there is a visible difference between what you get using the full fit with the derived RD and RD agnostic fit. So now this brings me to the most recent paper on this topic with my collaborators, 2 PhD students, Helena and Hamid, where we combined DAISY BAO with CMB lensing from the combination of Planck, ACT, and SPT. So this is the same combination as was recently used in another paper, and I'll cite it on the next slide. And the idea here is that CMB lensing, as well as galaxy-weak lensing and clustering, they provide a constraint on omega matter h squared. Now, CMB lensing doesn't just constrain omega matter h squared. There is a degeneracy between that number and also the amplitude of the primordial fluctuations, the AS. And if you allow for varying neutrino mass, there is a degeneracy with that as well. And this is the amplitude. So this is if you just constrain the amplitude, but if you have a very good control over the shape of the CMB convergence spectrum, you get additional information from the scale dependence. And you could get additional handle on AS and neutrino masses if you further combine this CMB lensing spectrum with galaxy-weak lensing and clustering. And we tested that neither CMB lensing spectra nor dark energy survey like 3x2 point correlation observables, that they're practically insensitive to the value of the sound horizon. So we can use them in our RD agnostic tests. Another option, this is optional, but nothing prevents us from using some additional information on the primordial amplitude from CMB, because not all of the CMB spectrum is sensitive to the sound horizon. For example, the information on Kobe scales is primarily constraining the primordial fluctuations, not necessarily sensitive to RD. So we optionally include a conservative prior on AS, which covers, again, a broad range of alternative recombination models. So it's inclusive of lambda CDM and modifications. And that, as you see, helps. And so with that, we can get a constraint on the H0. So this is a list of the data sets that we used. We used the AZ-BAO with the same theta star that I mentioned before, used as another BAO point with CMB lensing, which is the same data set used in a recent paper by Q et al. We used the year 3 DESI, it's DES year 3 likelihood for 3x2. We add the supernovae from Pantheon Plus, but as you'll see, they actually don't change anything. So we just wanted to include them with and without to see if they make a difference, but they don't. And that's because BAO alone constrains omega matter basically much better than supernovae at this time. And optionally, we include a Gaussian prior on AS. That's basically corresponds to this number, 304 plus minus 0.02. And this is what we get, just the highlight. So without the additional prior on the primordial amplitude from the current data, we get 70 plus minus 1.7. So that just between like 2.5% kind of measurement of the Hubble constant. If you add this conservative prior on the amplitude of the primordial fluctuations, the uncertainty gets down to 0.97 and the central value doesn't shift. So that's what we see. Of course, this is the uncertainties are not as small as you would get from CMB alone. But as you see, we also did a forecast and we have shown that there is promise for this approach to yield smaller uncertainties. So this is with a fixed neutrino mass at the minimal value of 0.06 electron volts, as suggested from neutrino oscillations. If you allow neutrino mass to vary, then that opens up an almost unconstrained degeneracy, unfortunately, at least in the current data. So all the uncertainties, especially on the Hubble constant, become quite large. Although if you have that additional prior on the primordial amplitude that I mentioned, they're still kind of not extremely large. It's plus minus 2.2. But you also notice that there is, because of this degeneracy, there is a bias towards larger values. Well, maybe it's real, but we've shown actually in our test that it's actually a bias towards larger values of the Hubble constant. And that's because of the fact that we sample neutrino masses using a uniform prior between 0 and some number, let's say 0 and 3 electron volts. We have checked that if we use the logarithmic prior, the values we get are pushed to lower, closer to 70. So it's because neutrino mass is essentially unconstrained, and how you sample it, the prior that you use matters. With experiments that constrain it better, that sensitivity to the prior choice disappears. And so these are results from our forecast. We used as our fiducial model the Planck best fit lambda CDL model, which is indicated here with dashed lines. And we used, so this forecast, I should say, is rather preliminary. We plan to do a more thorough job, but for now, we cooked up a few mock data sets. We used a mock data set based on the parameters of the completed DAISY BEO program. We used the Simons Observatory-like CMB lensing with a noise curve from one of the papers that corresponds to the target large aperture telescope, minimum variance noise. In addition, separately, we also tested the cosmic variance limited case for CMB lensing data. And similarly for this data, for the 3x2, we just shrunk the covariance by a factor of 25, essentially shrinking errors around all the correlators by 5. We kept the nuisance parameters as marginalizing over them in one of our tests, but we also did a test with fixed nuisance parameters just to see what happens in the most optimistic case. And we also added a supernovae mock data set, which would be something that you would get from LSST or Euclid, which is around 10,000 supernovae magnitudes, uncalibrated, and the same prior on AS, and the same theta star. And so the forecasts show that with a fixed neutrino mass, without an additional prior on amplitude of primordial fluctuations, you could achieve a sensitivity of between 1 and 0.7, depending, without this, basically around 1. If you in the most optimistic case, without AS, you get 1 if you assume cosmic variance limited and no nuisance parameters. But like I said, we will do a much more thorough forecast to see what happens with an experiment like LSST specifically. With AS prior, the same AS prior that we have now, you can bring down the uncertainty to as low as 0.57, which is coming very close to what we get from CMB using RD as a derived parameter. With varying neutrino masses, the constraints are weaker, but they do get closer to 1, plus minus 1, under most optimistic assumptions that we have used. So before I start on the topic of primordial magnetic fields, which I promised I'll give a bit of an update, let me also remind you why it's difficult to increase the value of H naught by just modifying the value of the sound horizon. It appears to be a welcome ingredient to solve the Hubble tension or to relieve the Hubble tension, but it's limited. And the reason is that the degeneracy in the RDH naught plane that you get from CMB is this red line at a fixed omega meter h squared. And if you climb up that red line, so you reduce your sound horizon, you climb up, you exit the BAO band before you reach the Shoes band. And so you have to choose whether to solve the Hubble tension with CMB or to creating a tension with BAO. So the sweet spot in this combinations of CMB BAO best fits is around 70, so 69.5 to 70.5. The only way around it is to increase the value of omega meter h squared. So if you move to higher values, then you can in fact reconcile all three. And that's actually what happens in models of early dark energy, which provide best fits with a higher omega meter h squared. But having such a higher value of omega meter h squared tends to increase the value of S8, and it brings it in conflict with weak lensing measurements, galaxy lensing measurements. So there is a bit of a constraint to how much of relief this kind of models can provide in general. So to summarize the first part of my talk, smaller sound horizon at decoupling appears to be a welcome, but not necessarily sufficient if the high values of 73 plus minus 1 persist, not necessarily sufficient ingredient to relieve the Hubble tension. But it also appears to help to alleviate the tension between baryon and CMB that's come about after the recent DAISY data. So a lot of work has gone into thinking what sort of physical models could produce smaller values of the sound horizon with the aim of solving the Hubble tension. And I worked on some of these models, but I think primordial magnetic fields proposal is slightly different in the way it was originally proposed and the way it's motivated. And that's because it was not introduced with the aim of solving the Hubble tension. Primordial magnetic fields have been studied for a long time. There is not a lot of new physics you can invent that could help you solve the Hubble tension. It's essentially a first principles approach, and it either solves it or it doesn't. But either way, it's an interesting topic. And as I'll emphasize again, whether you solve the Hubble tension or not, we want to learn something about primordial magnetic fields for other reasons. So why are we interested in primordial magnetic fields? It's a very old subject which traces its roots to Fred Hoyle and Zeldovich, and that concerns the origin of magnetic fields in essentially all clustered environments in our universe. So galaxies in particular, clusters of galaxies, filaments, and more recently, over the past 10, 15 years, also some evidence of magnetic fields in intergalactic space. I will not spend a lot of time reviewing all this evidence. I provided a brief summary on this page, but we see regularly papers coming out that point out that there is some evidence of magnetic fields that are not fully explained yet by astrophysical mechanisms. And again, let me emphasize that I'm not making a claim that all of the sightings of astrophysical magnetic fields cannot be explained using an astrophysical mechanism. In each of these cases, there are ideas and in certain cases, proven ways to generate magnetic fields. The point is that often you have to be quite inventive. So not all of these things can be, like, for example, not all different types of galactic magnetic fields can be explained with the same dynamo mechanism. It's different for different types of the galaxies. If you had primordial magnetic fields, then all of the sightings of the magnetic fields would be explained with one mechanism. So you would have to be much less creative in your astrophysical model building. So they are a welcome and a potentially very interesting solution to the origin of the magnetic fields, also because they would provide a window into the early universe. Because magnetic fields are expected to be produced in events in the early universe, such as phase transitions, like the electroweak phase transition. And in principle, in some modified inflationary mechanisms. I will not talk much about that, but there are ideas of how it could be produced there. And so if we get a constraint on them, it tells us something about the physics of the early universe. It's just to set some notation and language for what I will be talking about next. Let me review the main kind of vocabulary and facts about primordial magnetic fields. So first of all, we're talking about stochastic primordial magnetic fields. So it's not a uniform field that just points in one direction across the universe. It's a random tangled arrangement of magnetic field lines. As a working model, it helps to keep in mind the electroweak phase transition, because that's our working assumption in this work. So it was originally generated at some epoch and then remained frozen in the plasma. Magnetic fields have the property in a highly conducting plasma, they remain frozen in. So they scale with the expansion of the universe, just like radiation density. their density goes as 1 over a squared, and so the amplitude of the magnetic field B goes down as 1 over a squared. So density goes as 1 over a to the fourth. And they are stochastic, and we characterize their magnetic power, the amount of magnetic strength on a given wavelength, using a power spectrum. So here is there are two functions of scalar k, S and A. A corresponds to the helical component, parity odd component of the magnetic field. That can be very important, but for now I will not be talking about that. So let's just focus on S. And the power spectrum S is expected to have a power law form. For phase transitions, the form of this power law is well understood. The exponent is n equal 2, quite robustly. And for magnetic fields generated in inflationist scenarios, it's more model dependent. In the simplest models that were originally proposed by Ratra, Mike Turner, and others early on, it's scale invariant. And in this language, scale invariant corresponds to n equals -3. So electroweak phase transition or phase transition generated magnetic fields have a very blue spectra, with most of their power concentrated on small scales, and magnetic fields eventually dissipate, and so that peak of the spectrum keeps evolving as the smaller scales get dissipated and dissolved. So current state of the constraints on magnetic fields is summarized in this plot from a paper by Tanmay Vachaspati from about 5 years ago. On the y-axis is the strength of the magnetic field on a given length scale in Gauss. On the x-axis is the length scale. You can think of it as the inverse Fourier mode. And for example, a blue spectrum would have most of its power on small scales. And in fact, this dashed line corresponds to the prediction of the distribution of magnetic power from a power spectrum from phase transitions. That's the blue spectrum. While a scale invariant spectrum would give you a dotted line like this. Primordial magnetic fields have not been detected, so the amplitudes of both lines are unknown, but they are calibrated in a way as to give the magnetic field of a typical galaxy like Milky Way without any dynamo mechanism. So MW stands for Milky Way, and it's used as essentially a calibrator to set the amplitude in a rather arbitrary way, I admit, but it just provides you a guide on what sort of magnetic field strengths are needed to avoid dynamo mechanism in galaxy magnetic field formation. So you need about nanogauss or strength or below, just below nanogauss on, if it's scale invariant, it doesn't matter, but at least on kiloparsec scale. And then there are all the other constraints. There are upper bounds from BBN, from CMB anisotropies, like scalar vector tensor modes, perturbations, Faraday rotation. And there is this evidence that I mentioned earlier from the gamma ray astronomy, from blazars, that sets a lower bound, in fact, and that bound is dependent on the length scale. It's a bit, so the larger the length scale, the lower the bound, and the smaller on kiloparsec scales, it's about 10 to minus 16 or 17 or so. Also, how do primordial magnetic fields help relieve the Hubble tension? It's actually quite simple. The magnetic fields, they are, like I mentioned, they are inhomogeneous, they're stochastic, so their energy density is inhomogeneous. And so when they are present in a conducting plasma, they would push baryons into regions of lower magnetic energy density, and therefore create inhomogeneities in baryon density. And this would happen on rather small scales. This happens when photons and baryons are just starting to recombine, and on small scales, the sound speed drops becomes that of a viscous gas, as opposed to tightly coupled photon baryon plasma. And the fact that it's inhomogeneous, just that fact that you have inhomogeneous baryon perturbations, that speeds up recombination. I'll elaborate on that in a minute. And as a result, if you have an earlier completion of recombination, that gives you a larger Z star, so your recombination ends earlier, and the sound horizon, therefore, is smaller, and that's a welcome ingredient in solving the Hubble tension. So in terms of the equations, this is the relevant earlier equation in the regime that I mentioned. So as I said, there is a period just before the peak of the visibility function at around decoupling, where on small scales below the photon mean free path, L gamma, the speed of sound drops nearly to zero. And so instead of a tightly coupled fluid on the small scales, you now have a viscous compressible baryon gas. And the right-hand side here includes the Lorentz force term, which, if you write out, has this gradient of B squared term. So that term pushes baryons into regions of lower B squared, lowers magnetic energy density. And that's the source of the inhomogeneity. So plasma, as a result, develops density fluctuations. And these fluctuations grow, but they don't grow too much, because the effort the magnetic field puts into the generation of this inhomogeneities dissolves the magnetic field itself. Or if it doesn't, then eventually pressure counteracts, because the speed of sound is not entirely zero. So the amplitude is given approximately by this estimate, where it's order 1 at best. It's not linear, but it's also not very large. And the reason inhomogeneities enhance the recombination rate is because the equation for the electron density on the right-hand side has an n squared term, which is the product of the proton and electron densities, because they have to collide to recombine. And so because of this n squared, when you average, the average of an inhomogeneous n squared is always larger than the square of the average. So any baryon inhomogeneity would enhance the recombination rate, and that's the source of the sped up recombination. This was pointed out a long time by now ago, 12 years ago, by my collaborator Carsten Yudamzik and Tom Abel. And they, at the time, said that this is quite a significant effect that would put very tight constraints on primordial magnetic fields, which they estimated in that paper using a toy model, not a full simulation in magnetohydrodynamics, but a toy model that they invented at the time. So after Hubble tension became a thing, Carsten and I got together and tried to see if maybe that constraint on primordial magnetic fields could actually be turned into a detection. Maybe Hubble tension points to the need for such a reduction in a sound horizon due to inhomogeneities. So back in 2020, during COVID, we used the same three-zone model that Carsten and Tom invented. We call it M1 for just model 1, and used it in the standard Boltzmann code, CAM with RecFast, and computed the posteriors for all the parameters in this model. And that model had one parameter known as baryon clumping, defined as essentially the variance in baryon inhomogeneity. And at the time, we wrote a paper where we have shown that such a reduction in a sound horizon due to this results in a relief, not a full resolution, but a relief of the Hubble tension, as well as the SA tension at the same time. So since then, a major development was that instead of the three-zone model, we now are starting to get results from MHD simulations, thanks to very hard work by Carsten, Tom, and Ali Hamoud. So in particular, I should say Carsten put a lot of work into this using a modification of ENSO, a magnetohydrodynamics code, modified to work in a compressible regime and working with an additional chemical solver, which is similar to RecFast, that in real time computes recombination, the ionization history, and outputs it as a function of redshift. So as opposed to a three-zone model where there was no dynamics, it was a fixed, essentially a fixed probability distribution for baryon density that's independent of redshift. And this code includes a lot of the physics, like modeling of the Lyman alpha photon transport, which is quite important. I should say that this is a very computationally challenging and expensive project, which is ongoing. And at the moment, only preliminary sort of smaller, relatively small lattice results are available, and only for certain types of magnetic spectra. So we decided to focus on 4 possibilities: phase transition sourced spectra with and without helicity, so 2 possibilities, and a scale invariant spectrum with and without helicity. So all of these 4 are potentially very interesting to study. At the moment, we have results for just the blue spectrum version without helicity. And this is just what it looks like from the simulations. These are just pictures, but on the left, you see the magnetic energy density in homogeneity, and on the right, you see the projected baryon density in homogeneity from the paper by Karsten and others from 2023. Okay, but importantly for the Hubble tension, this work generated ionization history. So this is the relative difference in the fraction of ionized matter as a function of redshift relative to the standard lambda CDM output. And because it's so expensive to simulate this at every value of the magnetic field, essentially it's a separate simulation at the given initial magnetic field spectrum. So we did it, or Karsten did it at 4 values, and then we interpolate across 4 using linear interpolation. And also it's done at a fixed value of cosmological parameters, but we did test that when you do vary cosmological parameters around the best fit lambda CDM values, that is a minor impact relative to the change due to change in magnetic field. So we also we adopt the cosmological parameter sensitivity from standard lambda CDM to model the parameter sensitivity in the magnetic field version. And that's a tested assumption. So these are the results from a paper we produced in March of this year, where we used the data available at that time, which was Planck, DESY, DR1, with and without the prior from shoes. And we use essentially the magnitude from shoes combined with the Pantheon Plus dataset. Here, you can see that without a prior from shoes, we have no statistically significant detection of primordial magnetic field. There is a little bump in BPMF from the combination of Planck plus DESY. And I also should say that DESY plays an important role in the existence of this bump. It adds weight to it. As I mentioned earlier, it generally prefers a lower sound horizon. If you add the shoes prior, then you get quite a notable detection, which is around 3 sigma of the primordial magnetic field amplitude. The strength here is in terms of the co-moving field at redshift 10, which is very close to the redshift today. Magnetic field, as I mentioned, scales with redshift. It also, as it evolves in the plasma, it drops in amplitude. So if you want to find the corresponding magnetic field strength at the time of recombination, it's roughly an order of magnitude larger. Okay, so you could take an order of magnitude there. And the Hubble constant, predictably, in this case, doesn't go above 70, but it gets close. So if you look at the parameters with the shoes prior, you get up to 69.93 with a rather small uncertainty. So that's another nice feature here is that by adding model freedom, adding a new parameter, you don't inflate the error bars. You still get a tight bound. And the chi-square for the combination of Planck and Daisy is the same. So you get equally good fit in that case. And here there is, as you can tell, the Planck fit gets a bit worse. The Daisy fit gets a bit better. So the combination stays the same. Interestingly, this strength of the magnetic field that we get is very interesting just in terms of fitting all other sightings of primordial magnetic fields. It goes smack on to where you would want it to be to explain all the observed cosmic magnetic fields. The way to test this is to look at, well, one way, very promising way to test is look at a small scale anisotropies. And of course, additional data came from ACT-DR6 and SPT3G since the paper was published. And we will definitely use it in the next analysis of this model. But this shows the data prior to DR6 and SPT3G, and it shows that these differences were at the moment within the uncertainties, but it will be much more tightly tested. And I should also say that the challenge for us at the moment is to bring the theoretical uncertainties in MHD simulations in line with the increased accuracy of the data. So that's the big challenge. Let me also show a result from an ACT-DR6 paper where they analyzed both the toy model of baryon clumping and also more general modified recombination models, such as the MODREC model developed by Gabriel Lynch and others. And just very generally, they found that modified recombination models could help relieve the Hubble tension, essentially bring the value to around 70, which is also consistent with what we see with primordial magnetic fields at the moment. And so the plan for now is to pursue larger MHD simulations because we need to beat the theoretical uncertainties. Like you saw in the plot of the recombination histories that I've shown, there's quite a lot of scatter, and we use the mean values, which is a big assumption. It would be welcome if other groups perform the simulations, then we could do code comparisons. And as we speak, the data is evolving, both on the early universe side with new data from DAISY, ACT, SPT, eventually with Simon's observatory, and also on distance ladder measurements with the JWST data coming in and promising to eventually provide similar level uncertainties as the HST-based SHUS calibrations. So primordial magnetic fields are interesting because you can test this scenario. And even if you don't solve the Hubble tension, at least you'll constrain this very strongly. So other ways of confirm, if you were to see evidence from the Hubble tension type results, let's say this 3 sigma tension of primordial magnetic fields persists, right? How do we know it's that and not something else? So as I said, it would still have to pass the high resolution CMB, which is a big question, we'll see. But there are other ways to do it. If we ever convince funding agencies to fly CMB spectral distortion probe, such as PIXI or something of that nature, then spectral distortions provide another probe, which is through this cosmic radiation, cosmological recombination radiation, which is an effect that exists even in lambda CDM. But if you have additional magnetic fields, as Jan Schluber and his collaborators have shown, it adds a modulation to that signal that could be detectable. Earlier work have pointed out that mu and Y-type spectral distortions also offer quite a significant tight probe. So if you solve the Hubble tension or relieve the Hubble tension with magnetic fields, you would also see it with mu and Y distortions. So the amplitudes would be constrainable. Faraday rotation is unlikely to provide a tight constraint. Only if magnetic fields happen to be scale invariant, then there is some hope. And then this gamma ray astronomy can get close to probing from the lower end, like if it's really there and if it's a lower bound as opposed to an upper bound, then that lower bound could reach the range of magnetic fields that we're talking about. And the nice thing also is that if you see evidence from CMB for a certain magnetic field strength, that's a target. You can make then prediction for what gamma ray astronomy should be seeing. And then they will either see it or not. So it's a more concrete test. Other work on this, also notable work, includes possibility of this inhomogeneities affecting the growth of structure, in particular mini halos of dark matter. And it's a question whether they'll be detectable, but it's certainly an interesting topic to explore. So in conclusion, Hubble tension, as I said in the beginning, in my view, hints at a missing ingredient in the physics at the epoch of recombination. And the recently appearing tensions between BAO and CMB also appear to point to a slightly smaller value of the sound horizon. And this sound horizon agnostic measurements of the Hubble constant that my collaborators and I performed also point to the same range, although the uncertainty there is large enough to be consistent with all of the other measurements at the moment. But in the future, they'll offer percent level accuracy. And so that could be an important test, whether there is something interesting or new happening at recombination. And let me say at the end, again, that primordial magnetic fields were not invented to solve the Hubble tension, nor they are intended to compete with models like varying electron mass or early dark energy, which are interesting models as a possible solution. They are an interesting topic by itself. And so at the very least, this effect that I described is a first principle calculation, which will either help the Hubble tension or not. And if it doesn't, it will be the tightest constraint on the strength of the magnetic fields that we can have from cosmology. So at the very least, we'll have some input into what we can expect from the early universe. And I'll stop here. Thank you.
Thank you so much. Very nice talk. Any questions? Leandros?
Yes, thank you, Nora. I just wanted to, very nice talk. Thank you very much, Levon. Actually, I have 3 questions. The first question is, there are 2 ways to approach the CMB biotension. The first is to, of course, dynamical dark energy, and the other is to, as in your case, you said, to change RD, the sound horizon scale. Now, if you compare the 2 approaches, it seems like that the dynamical dark energy gives you a somewhat better fit than the change of RD. Can you give a physical reason why dynamical dark energy is preferred over somewhat preferred over change of RD, or it's not the case?
So indeed, dynamical dark energy gives a better fit. It also gives much larger uncertainties. In fact, I do have a plot with dynamical dark energy, which I'm happy to show. The same geometric consistency test that I have shown, I have a result with, so this is with W not WA. If I take RDH omega meta plane and analyze just BAO and analyze theta, you can see, so first of all, the uncertainties are generally much larger, right? And the peaks are no longer in the same place from the combination of BAO and theta and BAO alone, but the CMB alone constraint is now much broader. So the red line is just the theta star. Okay, so it just blows up all the uncertainties. That's one comment. So just looking at the chi-square can be a bit deceiving because you have also significantly increased the uncertainties. But yes, it gives a better fit. It also predicts a lower H0. So I'm not claiming that smaller sound horizon provides a better fit than the dark energy. It provides a resolution to the tension while also helping the Hubble tension. While the dynamical dark energy predicts a smaller H0. So it makes the tension worse.
Okay, thanks. My second question is the following. Can you show again this slide where you show dm over rd versus rd times h in the denominator?
Can you remind me, is it the equation or the plot?
Equation, yeah, the equation dm over rd with the integral, the integral of the distance. Yes, this I think. Yes, okay. Okay, now if you see this equation, you see that first of all, it's known that DESI measures somewhat higher distances compared to previous measurements of BAO of expected values from lambda CDM, from Planck lambda CDM. And so the equation is the following: if I put a larger number here on the left-hand side, I would expect a smaller number for RD times H. Yet, at least in the case of lambda CDM, yet what they seem to show is that RD times H is best fit is bigger. One would expect that to fit a larger distance, you just have to put a smaller value of RD times H. Yet the best fit is larger. Can you give a physical explanation of why this could happen? Because this is, I think, in your case also happens, right? In your approach.
Leandros, I probably won't be able to comment on whether the DESI points are higher or lower specifically. Of course, they come from different redshifts, and I can just refer to this plot where you can see how DESI data from different redshifts influences the value of H naught RD. And so some of them may prefer a lower H naught RD, but when you put them all together, that's where they end up. So each color here is essentially a measurement at a given redshift.
Okay, yeah, but if you actually see the numbers of the distances, you will see that most of them are larger. But anyway, it's not obvious why this happens, but I understand. Perhaps it's the integral of 1 over E of z that plays more important, because they see clearly some redshift dependence different from lambda CDM, which maybe plays a more significant role. And the third very quick question is, as you said, early dark energy requires a larger value of omega m h square, and that would violate, would be a problem with the, say, tension. Now, with the new kids data, this seems to have somewhat disappeared. Does this mean that early dark energy has gained points here, or?
Yeah, I would say it definitely reduces the problems for early dark energy. I have nothing against early dark energy. Like I said, I'm not competing to the best explanation of the Hubble tension. I'm genuinely interested in understanding this effect. Yeah, the tension, the SA tension has decreased. It's now, like, there was a paper by the kids collaboration just this morning or earlier this week. It's around 1.8 sigma, so it's not as significant, but increasing omega met H squared would increase it. So it provides a constraint. It may not be in tension, but it's still enough. It provides a constraint that you have to take into account. Yeah.
Okay, thank you, Levon.
Okay, thanks.
Thank you. And Lloyd?
Yeah, really nice talk, Levon. I just had a couple of questions if you have time, maybe, which were, well, one of them, I'm just curious about the amplitude of the baryon clumps on kiloparsec scales. So, in terms of delta rho over rho, how large are those in these models? How large is that
So
getting?
in terms of so the large, so they are, the effect is strongest at around kiloparsec scale in terms of the wavelengths that are most relevant, and in amplitude they are of order 1. So yeah, delta rho over rho of order 1. Yeah.
And might that have any other consequences? Seeding, could this potentially be seeding early structure, or
potentially, yes. So that's a very interesting thing to investigate. And I mentioned at the very end a paper by Ralengaka, Pranjal Ralengaka. That was a PRL where he investigated formation of dark matter mini halos due to this inhomogeneity in baryons influencing the growth of dark matter. I mean, there is some effect, I'm sure, that we suspected with Karsten at the time that it's likely to be small, but I really don't want to prevent anyone investigating it, discouraging. And I myself will look into it as well in more detail at some point. It could have some influence on dark matter growth, maybe. It's just quite a small, it's like giving an initial push, right? It's a small order one disturbance in baryons that doesn't then continue to grow. So it's like setting an initial condition, a rather gentle initial condition on small scales, and then dark matter would respond.
Right.
But it's not going to be an ongoing, persistent influencer on the growth. So yeah, that's all I can say.
And my other question was about the n=2 spectrum. And can you show that plot where you've got the Milky Way on it and the length scales? Magnetic field strength was the y-axis. Oh, I think you just passed it. Yeah, this. So you talked about getting an amplitude near the Milky Way for this n=2 spectrum. Is that the
It's the dashed line.
So you assumed a spectrum with n=2. How's the shape of that go as you go away from the Milky Way?
You mean how does it extrapolate to smaller length scales?
Or larger?
Or so yeah, so here it's going from smaller to larger, right? So I mean, it more or less continues in a, yeah, so for smaller scales, at smaller scales, the magnetic field would dissipate. So the spectrum would just be dropping to zero very rapidly. It's a blue spectrum rising up and then dropping because of dissipations. There is a like eddy turnover scale where magnetic fields start influencing, they depart from the frozen in configuration and start influencing the motion of baryons, so that allows them to dump energy. So there's like a gentle turn, and then there's a drop, because at some point they just dissipate. But on large scales, they carry on as an n=2. So towards the large scales, it's just a causality argument that says they should be the tail towards the large scale should be n=2. I don't know if that was the main thing in your question.
I was just trying to understand how that spectrum you assumed, comes onto this plot, other than just the one point. I don't know if you can sketch out what it looks like.
So okay, so if you start with an initial primordial magnetic field spectrum, you can estimate how much magnetic power there will be on a given scale. Yeah, at different redshifts, because that will evolve somewhat. So the dashed line is that prediction if the initial primordial magnetic field was a blue n=2 spectrum. And the dotted line is the prediction for a scale invariant initial spectrum.
Right.
Their amplitudes are arbitrary because we don't have a detection of a magnetic field. So we can only talk about the shape. But here they're just chosen to be, the amplitude is chosen for both in a way that on scales relevant to galaxy formation and collapse of the initial halo that formed the Milky Way or Milky Way type galaxy, that you could generate the magnetic field of that galaxy just through gravitational collapse of that primordial magnetic field.
Okay, thanks.
Okay, thanks.
Thank you. George?
Yes, sorry. So I think my one will be a quick one. So have you considered using full shape information to constrain omega MH?
Yes. And I know there is work on that I'm very well aware of and haven't cited. So the full shape would include the information on a turnover scale, the radiation matter equality, omega matter H squared, as well as BAO, the wiggles. And there are studies where they use the full shape and they essentially marginalize over the RD in those studies to just focus on. So they separate the spectrum into the broadband and wiggles and then marginalize over RD, get omega matter H squared. And then you can combine that with omega matter from supernovae, for example, to deduce H. And that's another RD agnostic way to get it. That method so far gives much larger uncertainties. The reason we didn't use the full shape was because it required, for one reason was that it required much more detailed modeling, like effective field theory type approaches to large scale structure. And there was no clean way to use the BAO information and the full spectrum without losing the information in a BAO that we wanted, that clean RTH omega matter constraint. So it was a choice, either use that or the other. But it's definitely something we thought about. And in the future forecast, we'll think about how to not miss on any information in a full shape spectrum.
Thanks.
Okay.
Thank you.
We can thank Levon again. Thank you so much.
Thank you, Eleonora, and thanks everyone.